Hi everyone, my name is Sman Narayan. I'm studying IB1, and in this video, I'm going to be talking to you about the Rutherford Goldfoil experiment and what its results were. So, what is the Rutherford Goldfoil experiment, you might ask? So, the experiment essentially tested the previous ideas of what an atom looks like and helped greatly develop our atomic theory. While the Rutherford Goldfoil experiment did not bring us the final form, it did bring us to a point where we could study it better. And I will be displaying a bunch of models to you today to explain what the experiment was and what and why exactly things worked the way that they were. Okay, so here we are at the diorama or the model of the Rutherford Goldfoil experiment. It's made primarily out of Legos, and I will go through each part of it, each component of it, step by step. So let's start with this box right here. This box contains a radioactive source that shoots out alpha particles, alpha radiation, in a beam that is represented in the red here. And this source is surrounded by thick walls of lead. Why lead? Because lead is one of those metals that doesn't allow any sort of radiation, be it alpha, beta, or gamma radiation, to penetrate its walls. That's just something that you should know. Lead is the primary metal used for the casing of the radioactive substance or the source. Now, as I stated, there's a beam of alpha radiation or alpha particles coming here and hitting a gold foil here, which is represented in yellow. And something strange happens. Well, some of the alpha radiation does, in fact, go through the gold foil in a straight trajectory here and hits the zinc sulfide walls or the fluorescent walls. Others don't do that. There's two different things that can happen. One thing is that there's a slight change in the trajectory, like observed over here. This one, of course, doesn't go in the same direction, but it's just a slight deflection into a different direction. And the other thing is that there's a complete bounce back of the alpha radiation. The alpha radiation hits the gold foil and then immediately goes in a opposite direction and hits this particular wall here. In the next segment, I will talk to you about why this happens with a molecular structure. Okay, so here we are at the second model that I've created here. This is basically a close-up look at the molecular structure of the gold foil, as well as the moving alpha particles represented with the string here. So, as I stated, there are three different things that happen. Either the alpha radiation or particles go right through the model. There's also the slight deflection that can be seen here. And there's, of course, the complete bounce back that can be observed here. So, why does this take place? This is because of the structure of how a molecule or an atom is made. So, the green dots here represent the nuclei of the different atoms of gold here. And the orange represent the area that the atoms use. So when a alpha particle is able to move from point A to point B without any deflection, this is because they're not encountering any obstacles in their path. They're able to go through the free space automatically to the other side and hit the zinc sulfide walls that are over there. Also, one thing we have to remember for the deflection point is that alpha radiation is positively charged, and nuclei are also positively charged. So, as we know, the laws of attraction, like poles repel each other, right? So, that's why over here, in this line, it reaches it very close to nucleus, and therefore bounces away, or not bounces away, it deflects in a different direction due to the laws of attraction. And of course, the last one, the complete bounce back, is because the alpha particle has actually hit the nucleus here and has to change trajectory all the way back. That's the reason why there's three different things that take place in the Rutherford Goldfoil experiment. And in the next segment, I will be talking to you about why or what the results tell us. Okay, so utilizing the three phenomena that take place, as well as the information that we've learned from the molecular structure, we can conclude that A, atoms are comprised of mostly empty space, and a majority of their mass, or an absolute majority of their mass, is concentrated in the nucleus, as I showed you back there. The rest of it is just empty space with the electrons floating around in orbits. And number two is that the nucleus is very dense, as I stated, and that's why it causes alpha particles to bounce back and completely change trajectory. And it also tells us, because of the positive alpha particles being slightly deflected because of coming in close contact to a nucleus, we can also conclude that the nucleus is positively charged. That means there are only positively charged or neutral charged subatomic particles in the nucleus in itself. And those things put together created the Rutherford nuclear model over here. Okay, so here's the top-down view of the Rutherford nuclear model. So, as I stated, the nucleus is the majority of the mass of a atom and is also positively charged. Most of the space is empty, and there are electrons moving in orbitals around the nucleus in this dotted space right here. The nuclear model and the results that came from the Rutherford Goldflow experiment replaced the previously existing Thomson plum pudding model, which was just that negatively charged particles were surrounding a positively charged cloud. Okay, a last portion I'd like to talk about is that Rutherford's nuclear model was not, in fact, the last model in the atomic theory. There's still Bohr's planetary model that talks more about orbitals and a more planetary, somewhat like a sun and planets, as the planetary system states. There's, of course, the quantum model, which is a little bit too hard to explain, but it was created by Schrödinger after Bohr, quite a few years later. So yeah, that was the Rutherford Goldflow experiment, what it is, what it does, how it was done, and what the results were, and what it accomplished in the process. I hope you enjoyed, and thank you for watching.